Good morning friends, and welcome to the next class of this video course on advanced hydrology. We have been looking at the chapter on atmospheric hydrology, in which we have already looked at the formation of rainfall and various types of models in which we try to find out what is the rainfall intensity coming out of a thunderstorm cell, and what is the average rainfall, spatial averaging, and so on. In the last class we had looked at estimation of evaporation using energy balance method. This is one of the analytical methods which we had said that we would look at in this course. Towards the end of the last class, we looked at couple of empirical methods, Roughness method and Myers method, and then we said that these two methods are based on the aerodynamic method, which we would look at in the next class. So, today we would start the lecture by looking at what is called the aerodynamic method. Okay. So, if we come here, aerodynamic method. We had seen earlier that the energy balance method uses two equations, two basic laws, that is continuity equation and the energy equation. And we saw that the energy balance method for estimation of evaporation accounts for one major factor which affects the evaporation, and that was the heat energy. Okay. However, there are many other factors or physical factors or hydrologic variables that affect the evaporation, all right, from a water body. The aerodynamic method accounts for two such other factors. What are those two? Well, we would look at them. Let me first say that the energy balance method uses the heat energy, okay, and the aerodynamic method, which we will see today, is based on two factors. One of them is the humidity gradient, all right. What is humidity gradient? We had seen earlier that there is a deficit of vapor pressure in the atmosphere, all right. So, depending upon the relative humidity in the atmosphere, you have certain vapor pressure, and corresponding to the existing climatic conditions, that is temperature, you have saturation vapor pressure. So, whatever is the difference, all right, that is what drives the movement of water from the water body into the atmosphere. Okay. So, that is one factor which is the humidity gradient. Okay. As we go up, how the humidity changes as a function of height. Okay. That is number one, and the other one is the wind velocity gradient. Either the wind velocity, or we can say wind velocity gradient, how the wind is changing as a function of depth. All right. So, these are the two basic driving forces for the formation of evaporation and then removal of the vapor, all right, which has evaporated away from the water body. Okay. All right. So, this wind velocity actually is what? It is the ability of the medium, it is the ability of the medium to transport the vapor or the water vapor away from the surface or the water surface, all right. Okay. And how about the humidity? Humidity, all right, dictates the ability of the environment, I can say, or the climate to convert liquid to gaseous state. Okay. We assume that the enough heat energy is available. Okay. Given the condition that you have the heat beating up, then how much will be the conversion from liquid to gas will depend upon the humidity which is existing in the environment or in the atmosphere. Okay. So, these are the two factors on which we would base our aerodynamic method. Okay. Now, what is this humidity gradient, all right, which will dictate what is called your mv dot, all right. Mv dot is what is the we call is the vapor flux. It is directly proportional to d of your qv over dz, okay, where mv dot is the vapor flux going upwards and humidity gradient is represented by dqv over dz. Okay. Similarly, the wind velocity will dictate what is called the momentum flux tau, and it will be directly proportional to du over dz. Okay. So, these are the two basic principles or laws of physics which we are going to use in developing the aerodynamic method equations for evaporation. Okay. Now, before we go to that, let me just try to explain you schematically what is happening. Okay. Let us say that this is your water body or the water surface close to the ground. Then what we do is we take any two cross sections, let us say Z1 and Z2 just above the water surface body. Okay. Then what is actually happening is water is getting evaporated, all right, this is evaporation, all right. Due to the heat energy and the humidity gradient, the water gets evaporated into the gaseous phase, and then because of the ability of the wind or the medium to transport that evaporated water away from the water body, you have some tau or the momentum flux taking place, and that is removed with the effect of the wind. Okay. So, what we will do is we will write try to write these expressions, all right. So, the first one is we will say mv dot is equal to negative rho a kw dq or dqv over dz, and I am going to number this equation as 3.5.11. Okay. Where what is rho a? It is the density of the air, kw is what is called vapor eddy diffusivity. It is a constant which depends upon the environment, okay, which dictates how much vapor flux would be there, and then qv, as you all know, is your nothing but the specific humidity. Okay. Now, this equation, all right, I am taking from table 2.8.1 from chapter 2, all right, and this was part of your reading assignment, in which you were supposed to look at some transport processes. Remember the convection, conduction and radiation. I said that the remaining things you go through on your own, and there is a table, please look at. So, what we are doing is we are drawing our knowledge from some of the things we have seen earlier. Okay. So, this is the equation which I have taken from table 2.8.1, all right, and in that equation the concentration C has been replaced by QV, all right, and it is given on page 44. Okay. For those of you who would like to verify this, can go to page 44 of the Ventichow's book. Okay. So, this is the basic equation which will govern the vapor flow rate depending upon the humidity gradient. Similarly, we will write, or we say similarly, the momentum flux tau upward through the plane or through any horizontal plane is given by, let me go to the next page, tau is equal to rho a k m and du over dz. We already said that tau is directly proportional to du dz, right. and let us say this is 3.5.12, okay, and in which your u is the wind velocity at height z. Okay. And what we will take do is we will take two heights z1 and z2, and we will take the derivative of this wind velocity and humidity gradient, and then try to derive this expression. Km is a constant in this equation, which is called the momentum diffusivity. Okay. It is the property of the medium or eddy diffusivity. Okay. And as earlier, its units are L square over T. Now, what we do is, now let us consider two horizontal planes at heights z1 and z2 such that they are sufficiently close to each other. Sufficiently close to each other. Why do we make that assumption? Well, the advantage is that whenever you have a non-linear relationship and you consider 2 points, all right, which are very close to each other, within those two regions or 2 points, you can assume the relationship to be linear. Okay. So, what we are doing is we are piecewise linearizing the problem, all right. So, we can consider the things to be linear within those two. So, z1 and z2 are close to each other. So, we can write the expression for the gradients, okay, using the linear assumption. So, that what you can do then is d of q v over dz is equal to q v 2 q v 1 over z 2 minus z 1, and similarly your velocity gradient will be equal to u 2 minus u 1 over z 2 minus z 1. Okay. Therefore, if I use these two expressions in 3, 5, 11, and I divide that by 3, 5, 12. Okay. So, what I do is I use these definitions of the gradient into the equations 3.5.11 and then 12 and divide the two, that will give me mv dot over tau. Okay. These are the two equations, is equal to rho a would cancel out, you have k w over k m times z 2 minus z 1 will also cancel out. So, you would have q v 2 minus q v 1 divided by u 2 minus u 1. Okay. Or you can simplify this and find out the expression for mv dot, that is where the evaporation is hidden, is equal to tau times k w over k m. You take care of the minus sign, and then you will have q v 1 minus q v 2, all right, divided by u 2 minus u 1. Slight rearrangement of the above equation. This we will call 3.5.13. Okay. So, this is the equation which gives us the mv dot in terms of the q v, that is the humidity at cross sections 1 and 2, and also the wind velocity at cross sections 1 and 2, and k w and k m are constants whose values can be calibrated or estimated somehow. However, there is one quantity on the right hand side of this equation which is still unknown, all right, which is this tau. Okay. How do we find this tau? All right. So, we still do have to do something, some jugglery here, mathematical manipulations to determine or estimate this value of this momentum flux tau. All right. So, what we are going to do next is estimation of this tau. Okay. What we will do is we would use, or we will use the concept of wind velocity in the boundary layer, okay, over the in the atmosphere, which is approximately 50 meters, okay, above the ground. All right. And how is that equation the boundary layer or the velocity profile described in the boundary layer? This we will take from our knowledge of fluid mechanics. All right. And this is described by u over u star is equal to 1 over k log of z over z naught, and this we would name a number as 3.5.4. Okay. I am sure you may have seen this equation earlier, and this is the velocity profile or the logarithmic velocity profile in the boundary layer, okay, where u star is the shear velocity, which is given by square root of tau over rho a. K is what is called the von Karman constant, von Karman's constant, whose value is taken as 0.4 most of the times, and Z0 is what is called the roughness height. Of the surface, which is the earth or ground in this case, for which one can refer to table 2.8.2. Okay. You can find the roughness heights for different types of land use patterns. Okay. Okay. So, we use this equation 3.5.14 for 1 and 2, okay, cross section 1 and cross section 2, or horizontal plane 1 and horizontal plane 2. We apply this 3.5.14 at these two horizontal planes. Okay. So that it will give you the velocity u1 and u2. Okay. You do that and then you subtract the two equations, what you would get. Okay. So, I am going to say 3.5.14, writing at 1 and 2 will give you u2 minus u1 is equal to, after certain simplifications, you have u star over k times natural log of your z2 over z naught minus log of z1 over z naught. Okay. It should be very easy to see. I have directly applied that equation. Okay. You can simplify that and it will be u star over k times natural log of z2 over z1, z naught will cancel out. Okay. So, what it gives you? It gives you u star. Okay. Remember, we are doing all this, why? We want to calculate or estimate tau, momentum flux, and that tau is hidden in the u star. Okay. U star is equal to square root of tau over rho a. Okay. All right. So, this u star then is equal to k times u2 minus u1 divided by natural log of z2 over z1. Okay. I have just come from here to here. Now, but u star is what? It is equal to square root of tau over rho a. All right. That means, you just simplify for tau, that will be your rho a times k u2 minus u1 divided by natural log of z2 over z1, all of that raised to the power what? Because there is a square root here, square. Okay. Now, substitute this expression for tau into 3, 5 and 13. Okay. What is 3, 5, 13? If you go back, this equation mv dot. Okay. Mv dot is what we are interested in. Okay. All right. Substituting into 3.5.13, what you would get is, I will give you the final expression as this, mv dot is equal to kw k square rho a qv1 minus qv2 times u2 minus u1, this whole thing divided by km of natural log of z2 over z1, and all of that is square. Okay. this is your final equation, and we will number it as 3.5.15. Okay. So, this is the final expression for mv dot or the vapor flux, all right, which is moving upwards and which is taken away due to the wind velocity. All right. It has considered two main concepts or two driving forces. One is the humidity gradient, other is the velocity gradient, okay, which are the two other major factors affecting evaporation. Now, on the right hand side of this equation, you see there are lots of quantities, all right, and it is not very easy to apply in real life. So, what people have done is people have tried to simplify this. Okay. So, what we will look next is or analyze is how we can simplify this, so that we can use this equation for estimation. All right. But before we go to that, I must point out that this is your famous equation, which is named after Thornthwaite Holzmann. That is the name of this equation. Thornthwaite Holzmann equation. It was developed by these gentlemen in 1939. Okay. Right. We need to measure QV, we need to measure U at different heights. All right. Also, we need to know rho A and various K's, different types of K's. So, there is lots of measurements to be taken or lots of quantities or coefficients to be estimated. Okay. Now, what we do is then we look at certain simplifications. Of this Thornthwaite Holzmann equation. Okay. All right. What I will do is I will list these simplifications one by one, and then finally derive or write the compact form of this equation. Okay. The first simplification is we get rid of these two coefficients Kw over Km, right. We say that this is constant, and fortunately it is close to 1. Okay. Both of these constants are close to each other, their magnitudes. All right. So, we can disregard their variations with respect to different climatic conditions, and we say that this ratio is constant and almost equal to 1. So, that we do not have to estimate both of them. Okay. Number 2, let us say U1 is 0 at Z1 is equal to Z0. What do we mean by this? This is a fairly reasonable assumption, wherein we are saying that the wind velocity close to the ground, very close to the ground, is equal to 0. Okay. Due to your boundary layer, you know that due to no slip condition, the velocity or the fluid velocity right next to a plate is 0 due to the no slip condition. So, we are trying to use that. We say that the U1 is 0 at the roughness height. Okay. Number 3, so that the U1 will vanish from this equation, we say that the air is saturated. This is another simplification or assumption that air is saturated with moisture where at Z1 is equal to Z0. Okay. Close to your water body, you are trying to find out evaporation from a lake or from a reservoir, right. So, right next to your water body or Z is equal to Z0, let us say in this case, you are saying that air is saturated. Okay. So, that you can measure the temperature close to the water surface body, and then you can calculate what is called the saturation vapor pressure. All right. And that will you can convert that into, or we can find out what is QV1. All right. So, QV1 and QV2 is the thing that appears in this equation. Okay. So, we are trying to simplify or estimate some of these things using these simplifications. Next simplification is we use the expression for QV, that is specific humidity, as 0.622 E over P. We have derived this already, okay, where E is your vapor pressure which we can measure in the atmosphere. How we can measure the vapor pressure? Well, we measure the dew point temperature and we use the equation for saturation vapor pressure. Okay, that will give you the vapor pressure. P of course is the atmospheric pressure, which we can of course measure. Okay. All right. So, measurement of E and P then will give you the estimation of QV. All right. Okay. And then what is relative humidity? It will be nothing but E actual over E saturated. Okay. We have seen this earlier. All right. So that you can have QV1 as 0.622 of your E sat close to the ground, cross section 1 is very close to the ground. So, you have E s over P, okay, at Z0, and then QV2 will be what? It will be 0.622 of your E actual at certain height divided by P at Z2. What is the change in pressure as you go up at cross section 2? We have this relationship. Once we know the pressure on the ground, we can find out its variation as a function of height. So, we have all those things. Okay. All right. And from here actually I can say then what is EA is your relative humidity times ES. Okay. We can measure the temperature at a certain height. We can calculate the saturation vapor pressure corresponding to that temperature, and once we have the relative humidity, we can find out what is the actual vapor pressure. Okay. All right. Now, what we do is we put all these assumptions or these simplifications back into 3.5.15, which is your Thornthwaite Holzmann equation, and simplify this. Okay. So, if we say that putting all of the above values or simplified expressions and equations, that is into 3, 5, 15, what do we get? We would have mv dot is equal to 0.622 of your k square. K is the von Karman coefficient, which is 0.4 times rho A, density of the air, times your E s minus E A, times of your U2, U1 has gone, and all of this divided by P is the atmospheric pressure, which can be measured, times natural log of Z2 over Z0. Z0 is the roughness height corresponding to different surfaces, and for water body it is given in the table which I just mentioned. Whole squared, and this is 3.5.16. Okay. Now, so this is your final expression for the Thornthwaite equation. However, we still need to find the rate of evaporation. So, what we do is we use the continuity equation, which we have seen already. All right. So, you have mv dot is equal to what? Is nothing but rho w times E A. Okay. And you are saying area is equal to unity. Okay. From a per square kilometer or unit area, you are trying to find out what is mv dot, or E A is the rate of evaporation from a water body based on the aerodynamic method. So, A here refers to the aerodynamic. Okay. So, if you put this thing in here, and so that you can have E A is equal to some constant B times E s minus E A. So, this is your compact final little expression 3.5.17, where what is the value of B? B is called a constant which combines all those things, 622 k square, von Karman constant 0.4 square times rho A times U2. Okay. So, it is taking care of the wind velocity, the density, lots of the factors, over the atmospheric pressure, rho w, and natural log of your Z2 over Z0 whole square. Okay. And we say that this is 3.5.18. Okay. So, this combination of 3.5.17 and 3.5.18. So, this is your final aerodynamic method or the Thornthwaite Holzmann equation for estimating the rate of evaporation from a water body, a lake or a reservoir, in which we just need to calculate some of or measure the humidity and temperature and pressure and vapor pressure, these things, and we can calculate the rate of evaporation. Now, you see that on the right hand side there are two things that appear. Okay. One is the vapor pressure deficit, that is ES minus EA, and other is the wind velocity as far as the physical factors are concerned. So, we have already seen the empirical equations. Okay. So, what I am going to say is that many empirical equations are based on this I am going to say aerodynamic method equation, aerodynamic method, Thornthwaite Holzmann equation. For example, what are those empirical equations? Well, yesterday we have looked at Myers formula, okay, and other one was the Roughness formula. Okay. There are many more, but these are the two we had seen yesterday. Okay. So, you see that this is the most general or the mother of all the evaporation equations, the Thornthwaite Holzmann equation, and many empirical equations are based on this aerodynamic method. Okay. Now, what we will do is we will move on and look at what is called the combination of these two methods. Okay. So, we have looked at two analytical methods, one is the energy balance equation or energy balance method, and the other one is the aerodynamic. All right. So, now we will look at what is known as the combined aerodynamic and energy balance method. Okay. Okay, as the name suggests that we are combining two methods here. Okay. One method accounts for one factor, all right, physical factor that affects the evaporation, which is the energy balance method, which takes care of the heat energy. There is other method which accounts for two more factors, which is the humidity and the wind velocity. All right. All three are important, but however, many times what happens is sometimes the wind and the humidity gradient may not be that important, or heat energy is the only important thing, all right, or the predominant thing I should say. In those cases you can use the energy balance method, all right. In other cases where the energy is not so important, but the winds and the humidity gradient are predominating factors in a particular climatic conditions, then you can use the aerodynamic method. However, it is not easy to find out the conditions or situations where either of these two methods can be used very accurately, okay, because all the three physical factors are important. All right. So, what we do is we try to combine or we try to exploit the advantages of both the methods. Okay. So, let me write it down then. Aerodynamic method uses wind and relative humidity controls, okay, or aerodynamic method is used when these factors control in the actual life, real life situation, and the energy balance method is used when the heat energy controls. Okay. However, normally both or this all three factors control. means some combination is needed. Okay. Now, when we talk about this combination, all right, what we will do is we will not only combine these two methods, but we will also look at one key parameter, which is the sensible heat Hs, which we had not taken care of when we derived the energy equation. All right. So, what we will do is this combined method which we are going to develop will not only be accurate as far as the being able to account lot of factors right while deriving this equation, but also it will take care of Hs, H subscript S, which is the sensible heat loss back to the atmosphere in certain form, because that is very difficult to estimate. Okay. So, let us look at that. Sensible heat energy which we had neglected while developing the energy balance method. Okay. Hs, as I said, is difficult to measure. Okay. So, what we will do is we will account for this Hs indirectly. All right. So, this combined method will be able to account for Hs indirectly. That is, we do not have to measure it, but we will account for that using some mathematical manipulations. Okay. So, let us look at that for Hs. What is Hs? It is the sensible heat flux, all right, through the air, okay, physically by convection. Okay. It is the sensible heat flux which goes back into the atmosphere out of the Rn that comes in, all right, through convection. So, that is the physically what this physical variable is. Okay. Similar to that is what we have Lv m dot V is what? It is the vapor flux. Okay, we have seen that already in the aerodynamic method. It is the vapor flux through the air by convection. Okay. So, what we are trying to do is we are trying to say that Hs, that is the sensible heat flux process, and the LV dot, or which is the vapor flux process through the air, they are similar processes, okay, because they are caused by the process of convection. All right. So, we say that they are similar processes. So, we can take them to be proportional to each other. Okay. Why? Because both of these processes being caused due to the convection in the air. All right. So, whatever is the convective condition that will dictate Hs, that will also dictate the vapor flux. All right. So, what we say is that if we take the ratio of these two, then that will be constant. All right. And then we try to find that constant. So, once we know one part, we would know the other one. Okay. All right. So, then we define, or let us then define a ratio which is called Bowens ratio, beta. How do we do that? It is the ratio of Hs and LVMV dot, that is all. All right, which is we say 3.5.19. Okay. So, with G is equal to 0. Okay. So, we still make the assumption that the heat loss to the ground is 0, or we are not able to measure it, but that is actually quite reasonable assumption, because G as compared to Hs and Rn is very small. So, we can make that assumption still. All right. So, that means your energy balance then looks like your R n minus H s minus G is equal to L V m dot V, and we say that G is equal to 0, and what is L V m dot V? We have just said that is beta times H s, okay, using the definition of the Bowens ratio. Okay. So, if you simplify that, then you will have R n is equal to L V m V dot times 1 plus beta. Okay. So, you see that in R n we have incorporated beta, which incorporates H s or the sensible heat loss. All right. So, we are indirectly accounting for this H s without actually having to measure it. Okay. And let me number this equation as 3.5.20. All right. All right. So, now the only problem is how to calculate or estimate this beta. Okay. Right. For this, what we will do is we will use two transport processes, similar to the two transport processes we had used in deriving the aerodynamic method. Okay. So, in this case, what we will do is use two transport processes. Okay. So, let me be more specific. In the Thornthwaite's method, Thornthwaite Holzmann equation, in deriving that, which were the two transport processes we used? One was the vapor transport and other was the momentum transport, right. We had said that vapor, first the liquid gets converted into vapor. So, there is a vapor transport taking place, and then once the vapor gets accumulated, it is transported due to the wind action. All right. So, we looked at the momentum transport, and for the Bowens ratio or for estimating the Bowens ratio, we will use the two transport processes which are involved here, which is vapor and the heat transport. Okay. All right. So, we have already seen what is m v dot. It was we had taken while deriving the aerodynamic method as this equation, and I am going to number this as 3.5.21, and the H s is minus rho a C p k h d t over d z. All right. This is 3.5.22. Okay. And all of these are coming from your table 2.8.1 from page 44, which we had seen earlier. Okay. So, these two equations correspond to the two physical transport processes for the transport of heat energy. One is the m v dot, which is for the vapor transport actually, and H s is for the sensible heat transfer. Okay. I will not go into the details of this. You can look at these equations and the associated material. Okay. However, let me define what are the quantities in the second equation, where C p is the specific heat at what? Constant pressure. Okay. K h is the heat diffusivity, all right, and temp T is of course the temperature. All right. So, this H s actually depends upon what? It is a process of convection, right. So, it depends upon the d T d z, or how the temperature is varying as a function of height. Okay. So, H s is directly proportional to d T d z. All right. Now, what we do is we consider the two planes at z 1 and z 2, all right, and do a very similar analysis. Okay. That is, you will have H s over m dot v. You take these two equations, divide each other, what you will have is this C p k h T 2 minus T 1 divided by k w of your q v 2 minus UV1. Okay. Let me go back. You divide this by this, dQV over dZ is you have taken as QV2 minus QV1 over Z2 minus Z1. Similarly, dt dz you have taken as T2 minus T1 over Z2 minus Z1, and you divide these two equations, things will cancel out, and this is what you will get. So, this is 3523. Okay. Now, let us put QV as 0.622 of your E by P and divide by LV, all right, this equation, right. In 3.5.23, the operation we are doing is we use QV is equal to 0.622 E by P, and then we divide this equation in the on the left hand side, if you see, it is HS over MV, all right. So, if we divide this by LV, we will have on the left hand side what? HS over LV MV dot, which is equal to what? The Bowens ratio. That is what we are trying to find out. Okay. All right. So, what we will have is Bowens ratio beta is equal to HS over LV MV dot is equal to what? This whole thing, Cp KH P T2 minus T1 divided by 0.622 of your LV. You can verify that Kw and E2 minus E1, okay, or you say beta is equal to some gamma, all right, times just the physical variables which you will measure, T2 minus T1 over E2 minus E1. Okay. This you say is your equation number 3524. Okay. And this gamma is called the stoichiometric constant, which is Cp KH P over 0.622 LV Kw. Okay. This is 3525, which is the definition of your gamma. Okay. So, what have we done so far in the combined aerodynamic energy balance method? The only thing we have done is we have taken care of the sensible heat HS. All right. We have said that in the energy balance method we ignored it, and we said that we can take that equal to 0, but in many practical situations you cannot ignore the HS. All right. So, what we have done is we have gone around the two physical processes, and then we have estimated HS in the form of Bowens ratio, okay, which has come out to be equal to or given by this expression 3.5.24. Okay. Now, in terms of all of these parameters, what people have done is they have shown, or we will write that now it can be shown or derived that your combined evaporation is given by this equation, delta over delta plus gamma times ER plus gamma over delta plus gamma times EA. Okay. It is a simple combination. Actually, you see that this is a weighted average, all right, of the two evaporation rates, and let me number this as 3.5.26. Okay. So, in this equation what we are saying is that the rate of evaporation E, all right, has a certain weightage. Okay. This is ER. ER is what? ER is the energy balance method. Okay. This EA is what? EA is the rate of evaporation calculated using the aerodynamic method. So, we are combining these two and we are giving them different weightages, all right. One weight is delta over delta plus gamma, other is gamma over delta plus gamma. Okay. And you see that the sum of these two weightages is equal to 1. Okay. Now, what is this delta? Well, we have seen already delta is nothing but the slope of the saturation vapor pressure curve as a function of this temperature. this we have seen already the beginning of this chapter. Okay. All right, and gamma we have seen already derived above. Okay. And let me write simply that or simplify that R ER is equal to Rn over LV rho W, this we had derived already, and EA, this is your energy balance. And EA is capital B times ES minus EA, we had just derived, which is the aerodynamic method. Okay. So, this is your final expression then 3.5.26, which combines the energy balance and the aerodynamic method, which is the most accurate method, as it is able to account for both the methods. Not only that, but it is also taking care of the sensible heat Hs. Okay. All right. So, what we are going to do, the last thing in this chapter or the next thing in this chapter is we would look at what is called the evaporation over large water bodies. Okay. And this is what is actually called Priestley and Taylor method. And this was proposed by these two gentlemen in 1972. Okay. What they have done, these two gentlemen, is that they have conducted many experiments, all right, across many different types of lakes of different sizes and shapes and in different climatic conditions. Okay. And what they have found is some interesting observation, all right. They have tried to combine the two methods. So, they would find out the evaporation from the lakes, all right, using the energy balance method and also the aerodynamic method. And then they found that the ratio of these two methods is a certain percentage of the other. Okay. So, what we will do is, let me write it down. Their observation is that the energy balance considerations govern the evaporation. Okay. They said the main factor for causing evaporation is the energy, right. After that you have the other factors which will be certain fraction, although they will be important, but the major factor is the energy, all right. The other conclusion they had was that they found that the second term in your combined method is about or approximately 30% of the first one. Okay. What is the second term? Well, the second term in your combined method is the aerodynamic term, right, which is which has a certain weightage times EA, and EA is the rate of evaporation estimated due to the aerodynamic method. So, what they are saying is that the importance of the aerodynamic method is about 30% of the importance of the energy balance method, all right. So, if you use that expression or their conclusion, then you can say that the combined evaporation E is equal to alpha times delta over delta plus gamma. Okay. What is this factor? Delta over delta plus gamma. This is the weighting factor for the energy balance method in your combined method, if you see, and we have put an alpha in front. Okay. What will be this value of alpha if the weightage of the second term is 30%? Well, you have the 30% here and 100% here. If you sum the two, it will be 1.3. So, you see that your value of alpha will be 1.3. So, what they are actually saying is that for the large water bodies or the large lakes, all right, you actually do not have to make a lot of measurements which are involved in the aerodynamic method, all right, your QV, the wind velocities and pressures and so on. You can take advantage of the aerodynamic method by this observation which they have made, all right. So, if you look at this equation, all right, excuse me, and let me put that this is equal to E R. Okay. E R is the due to radiation or the heat energy. So, what they are saying is that the evaporation is equal to 1.3 times this factor times E R, and E R involves only one measurement, which is the net radiation, you see. So, we are able to account for all the factors without actually having to measure most of them. Okay. This is the major advantage of this Priestley and Taylor method, which gives you quite accurate results as far as the rate of evaporation is concerned, and you do not have to measure a lot of these physical parameters. Okay. So, with this I think we come to the conclusion of this chapter on the atmospheric hydrology or atmospheric water. Okay. In the next class we would like to start the next chapter, which is on the surface water. Okay. So, with that I would like to close today's lecture. Thank you.